Hi, welcome back to the Modular Bench Power Supply project. In the past videos, we've covered pretty much all of the individual modules that would make up a bench power supply, with the exception of the power input stage, which would be a transformer, rectifier, capacitors, or using a second-hand laptop power supply adapter or something like that. We're still not going to cover that off just yet, but what I want to do now is to actually put together all of the modules we've covered so far and get our first basic power supply up and running. This won't include a display output, but I've already covered off a little bit about how you can attach those. But what I do want to do is get at least a power supply circuit working that would be aimed more towards the student and the beginner electronics enthusiast. So to that end, what I've got on the board here now is we've already covered the theory of op amps. This one I've drawn here. I haven't finished connecting it up yet because I want to go through that as we do this video. The first one is allocated for controlling the voltage. I've kept with our standard 10:1 divider ratio here. The second op amp is to control our current, and I haven't got a feedback dropper here because what I've done is I've added an OR1 resistor, so a 100 milliohm resistor, in series with the output negative connector to the power supply ground. The FET, which we talked about in the last video, I'm using here is connected to the positive rail, which will be our 30 to 40 volt main supply rail, and the source is going straight to the output. What I've got on this side is basically our 5 volt reference, so using a Ref 02 as an example to give us a very stable voltage reference of 5 volts pretty much exactly. And I'm using a 10-turn potentiometer to drive the input to the voltage op amp. I'm also using a 10-turn potentiometer to drive the input to the current amplifier, but what I'm doing in front of that is putting a dropper resistor so that I effectively get a 10:1 ratio across the current output. So we have a 5 volt here, we basically have a 10:1 ratio here so that we get a 500 millivolt range available to the input of the current amplifier. And the reason for that is because we're going to sense the current that's going through our load using a 100 milliohm resistor. So a 100 milliohm resistor, 500 millivolts out, which would be our feedback, would give us basically 5 amps. Now I'm using these values because they're, well, simply easy numbers to use and to do math in your head and things. So you can adjust the voltages and the dividers to suit whatever range you want to have for your power supply. Just for the sake of this, I'm going to use the 500 millivolt range going into the current, a 5 volt range going into the voltage op amp. And so if you remember the math we did before, 5 volts going into here, it's a 10:1 ratio, so technically we would have a 0 to 50 volt control capability because of the 10 times gain which would be induced because of the divider network on the voltage side. Now our rail only goes up to 30 or 40 volts, so we're never actually going to get the 50 volts, but it allows us, using the 10-turn potentiometer, to get a fairly good range. An easy way to change this, if you were using say 30 volts and you wanted to make sure that your potentiometer maxed out at 30 volts, would be simply to take your voltage reference, in this case 5 volts, and make a 3-to-2 basically divider, so that you would have 3 volts across your potentiometer and just drop 2 volts across a series resistor. That way you would have an input range to your op amp of 3 volts. Then when you can have an output of exactly 0 to 3 volts. Same thing with your current reference voltage going into the current op amp. Just by adjusting the ratio here, you could potentially make it, instead of going 5 amps, if you did a 50:1 ratio on this, then basically you're going to use 0 to 1 amp here. You would just get 0 to 100 millivolts here before this thing would be basically saturated. So you couldn't control more than about 1 amp. But anyway, for now, as I said, just for the easy math, I'm using a 10:1 ratio here, 10:1 feedback over here. The resistor, which I haven't marked yet here, is 100 ohms. And the diode here would be any fairly standard jelly bean diode, so say a 1N4001 or a 1N4148 would work as well. You'll see in a minute when, or if you've been following on Element 14's forum, we've been doing some math with a few people asking questions. I put the circuit diagram up that I'm about to go through a few days ago so that you could have a look at it and see if you could figure out yourself how it's going to work. So anyway, that being said, let's start connecting up the rest of these wires for this circuit. Now I'm going to use a orange marker just to finish the connections. So our voltage circuit, I've already gone through once in a previous video the basics of the voltage control circuit and connecting a FET to it. We've got a 10K series resistor from the output of the op amp. Now if you remember, there's no current going into the gate of the FET except the fact that it behaves like a capacitor, so you have to charge it up. Once it's charged, there is no current flow, so a 10K allows you to limit the rate of change going into the FET and prevents it ringing and things with fast transient changes on the input. So we're just going to connect that to here. Our V-Sense feedback, if you remember, came from the output terminal of the power supply, so that would connect here. Now without any further connections, and of course this going to ground, we're now able with this simple circuit to be able to control the output of the FET from 0 volts up to potentially 50 volts, but basically to the limit of your supply rail, less a little bit. If you've been doing some experimenting, you'll have already realized that with the output of this op amp, even if this goes to the full rail, if you're using the same rail as the FET, so let's just say it's 30 volts, you need to have about 3 or 4 volts between the gate and the source to be turning the MOSFET on before you even start driving any high currents through it. So in order to achieve that, what you need to do is have either a higher rail or accept the fact that your output is probably going to be a little bit less than the supply rail by a few volts. So if you have 30 volts, which is what we're going to use on the bench shortly, although I may series up 2 of my outputs to get a higher voltage range, you'll see that the maximum output I can actually get is probably about 25 or 26 volts, because my op amp won't quite go to the positive rail because of the one I'm using at the moment. And you have to have about 3 volts, like I said, between the gate and the source in order to turn the MOSFET on. So between the two, you're going to lose maybe about 4 volts from whatever the supply is. Now, we're going to vary the circuit after we've gone through this first one so that we can actually achieve a much, much better control of this. But for now, we're just going to go with the basic circuit. Now, for the current side of things, so obviously this is going to drive up the gate, turn on the MOSFET, and your output is going to be providing whatever current pretty much that your load needs. Now you don't want to let it go out of control. You want to be able to limit the current, one, because if you put the wrong voltage onto something, you don't want to blow it up if you can help it, and two, if you want to limit the current, right now with what's currently connected, there is no way of doing that, and you don't want to start blowing fuses or damaging components in your power supply either. So the easiest way to do this is actually to sense the current using a resistor in series with your load. So remember, this is our high power rail up here, the V++, which is 30 to 40 volts. It comes through the MOSFET and out to your load. When it comes back through the load, I've got this resistor here before it goes to the negative rail of the power supply. And this is 100 milliohms. So 100 milliohms, 5 amps will give us 500 millivolts. That 500 millivolts matches what we're going to be putting in to the positive side of this op amp. All right, so let's take the negative side and let's just connect that to the top end of the resistor. All right, now remember, the op amp itself is powered by the same supply as this, so I'm not going to draw, well, I can draw it in, I guess. Okay, so what's going to happen now is as the current increases, the input to the negative side of this op amp is going to increase. The minute it exceeds the positive, this op amp is going to start driving negative. Because remember, the op amp will always try to do what it can to keep its inputs the same. Now, if the input here on the plus side is, say, set to 100 millivolts, then it wants to have the negative input at 100 millivolts as well. Now, I've put a blocking diode here for a reason, and if you haven't figured out what that is yet, and some of you have, then I'm going to tell you now. If I didn't have this here and I connected this straight to the gate of the FET, then if your current wasn't reaching the volts that you wanted in order to get the inputs of the op amps the same, it's going to drive its output higher and try and do that. And what it's going to do is it's going to fight with this op amp and push the gate voltage up. This op amp would then try and pull it down, and basically it's going to settle at some middle value, or one of these is going to be hitting the top rail. So putting a diode in here so that the only direction that this op amp can take current is taking it away from basically this junction here, which, because the FET, as I said, doesn't really have any current going through it, it's a voltage controlled resistor in a simplistic term, it's going to pull the current that's being delivered out of the voltage op amp through the 10K down through the diode, through the 100 ohms, and into this op amp. All right. Now, if you, as I said, if we've set 100 millivolts on the positive input, this is going to want this to be at 100 millivolts on the negative input. The only way it can do that is it's going to try and drive its output as high as it can. Because there's a diode here blocking it from forcing the op amp any higher than this op amp has already set it on the MOSFET, then it's going to have no effect whatsoever, and the output of this op amp is going to go basically to the positive rail, so 29, 28, 30 volts, something like that. The diode is going to prevent it from driving the gate of the MOSFET high. As the load increases, which would increase the current through this resistor, or you basically increase the voltage going out, which again, if you've got a fixed resistance or as your load, would again increase the resistance, the current going through this resistor, then the voltage on here would slowly increase. All right, so you're going to start off with a low voltage, and it's going to be creeping up as your current goes up, and it's going to be representative of the current. We've got 100 millivolts set on here representing 1 amp. So as this approaches 100 millivolts, which would be, of course, 100 millivolts across this center resistor representing a 1 amp current, then the output is going to start going towards 0, because as long as these two inputs are balanced, the output of this would go to 0. All right. So as this becomes closer to this is going to start driving away from the positive rail, and at a certain point it's going to start pulling current down through here to pull it down, because it's going to be trying to stop the negative input going above the positive input. The result of this, because you've got 10K here and you've got 100 ohms here, the current is limited basically by what can go through this 10K, through the 100 ohms and down here. So you've got about 100,100 ohms. That works out at around about 230-ish microamps. So across here is only going to be 23 millivolts. You're going to get about 700 millivolts dropped across this diode. It may be a little off because you've got so little current actually flowing through it, but it's enough because of this limiting to pull this voltage way down and start turning this MOSFET off. The effect of that is that it's going to obviously reduce the voltage on the output, and if this has already come up enough to get 100 millivolts on here, it's going to keep this balanced. So as long as your power, your voltage output is higher on your voltage setting than what your current wants through your load, then you're now going to be in current limit mode. All right, and you can control the current by adjusting this potentiometer down here. The minute that your load voltage side, if you started, if you were in current limit mode where you had 100 millivolts across here, you had 100 millivolts in, if you reduce this voltage setting here, say maybe you had 10 ohms over here, all right, which means that you've got 10 volts on your output to get your 1 amp. This is now sitting just on current limit because you've set your 100 millivolts here. You have your 1 amp flowing through with 10 volts. You've got your 100 millivolts back in here. It's going to be stable. It's going to keep it current limited. If I tried to turn this voltage up to go from 10 volts to say 20 volts and put 2 amps through, because this is set, this is being fed back to here, this is going to turn harder on and prevent the voltage on the gate from going up to allow that voltage to come on any harder. If I turn this voltage down from 10 volts, and maybe I try to set 5 volts, now 5 volts into 10 ohms is only going to be 500 milliamps. So that's going to actually now reduce this current down to 500 milliamps through here and only give us now 50 millivolts on here instead of 100, which means that this input is now lower than the positive. this output of this current limiting op amp is going to drive high again, trying to turn on the MOSFET to actually increase the voltage to increase the current. The diode is going to prevent it from doing that because we don't want the current side of things. Remember, it's a current limiting circuit, not a current controlled, like a DC load. You may want to control the current, or if you were using a precision current source, then you'd want to control the current and be able to drive it up and down as well. In this case, we want to use it as a current limit. So the diode is there to prevent this current limit, when it's not in limit, from driving the output of the MOSFET any harder on than what the voltage regulator is doing. So that's pretty much it for a very basic student power supply. So you've got your 30 volts, you've got a current sense resistor, you've got your MOSFET output. Now that could also be just as equally a bipolar transistor, like a 2N3055 or one of the tip series, depending on how much current you want. So you can literally pull this out of circuit. You could drop in a Darlington driver pair here, and you may have to adjust this resistor coming out of this op amp so that you have enough current flowing through here in order to be able to have the current gain. Because remember, a bipolar NPN a Darlington array, it's a current amplifier, not a voltage amplifier, and it's running in common collector mode, or emitter follower, sorry, as it's normally called. An emitter follower NPN transistor will effectively self-regulate itself. If you try and change the load, if the base is set to say 10 volts, you've got maybe 1 or 2 volts dropped across the base emitter junction. It's going to effectively adjust its current flow through from the collector to the emitter in order to keep this 2 volts or 1 to 2 volts drop between the base and the emitter constant. So as I say, it's a current amplifier, but it's working at, it's effectively got its own negative feedback, which allows it to stabilize and keep the voltage output fairly constant. So anyway, that's basically the circuit that I'm about to go across onto the bench. I've got it already set up on a breadboard and a few things floating around off the breadboard. So let's go over there and have a look. I've got a whole bunch of meters set up so that we can probe various outputs and control points on this circuit so we can see what's happening. So let's get over to the bench. Okay, now we're at the bench. Just before we start, I decided to draw up the circuit diagram that I'm using so that I can show you exactly what we have and what we're going to be testing. So first of all, I'm using a Ref02 precision voltage reference. It gives out 5 volts on pin 6, and it can take up to 40 volts on the supply rail. That output on pin 6 is feeding a 10K 10-turn potentiometer into the voltage op amp, and it's also feeding through a 500K and a 50K 500K resistor and a 50K 10-turn potentiometer to ground, so that the output of that potentiometer basically goes from 0 to 500 millivolts to the positive side of the current op amp. Now, as you'll see in a moment, these resistors, the 50K is a proper 50K 10-turn potentiometer, but I don't have any 500K resistors, so I've made it up using 5 100K 5% resistors. So it's not going to be exactly 500 millivolts, but it's going to be close enough. The output over here of the power supply, so here's my power MOSFET that's driven off this power, this bus positive rail through the MOSFET to the output. This is the output is being fed back through a 100K and then an 11K. Now again, I don't have an 11K at the moment, so I've made it up with a 10K, a 1K, a 100 ohm, and a 10 ohm resistor. So it's giving me as close as I can as a 10-to-1 ratio between the feedback op amp R11 and R10. So it's giving me a roughly 10-to-1 feedback. It's not exact, but again, it's close enough for what we're dealing with here. If I have some precision dividers coming from Vichy, they just haven't arrived yet. They may not be here for another couple of weeks, so I didn't want to delay doing the tutorial for the basic power supply that long. And again, because of the tolerances, and with this kind of simple power supply, you would usually be adjusting your voltage based on what you are reading on the output versus trying to set a dial without some kind of visual aid to the exact amount. So having it roughly correct is probably still, again, close enough. My current op-amp, as you can see here, has got the 100 ohms. I've marked this a 1N4148, but right now I have a 1N4007 in here. It doesn't make any difference. Any diode will work. Don't make the mistake that I did the first time. I accidentally put a Zener in here, and I was trying to figure out for about 5 minutes why things weren't working properly until I realized what I had done. The minute I put the diode, the correct diode in, everything started behaving correctly. And that output is fed up to the gate of the MOSFET as well. So you've got the 10K feeding the MOSFET gate, and you've got this diode through 100 ohms to the current op-amp, which will back it off if the feedback starts indicating that we need to apply current limit. Here is our 100 milliohm resistor, which is providing our current feedback to the current op-amp. And that basically completes the circuit. Another important thing I want to just point out here, and I've made a very clear example of this in the way that I've drawn the schematic, is you want to keep your power bus rail separate from your supply rails for your monitoring and feedback circuitry. See here, I've got my 3 smoothing capacitors. If this was being fed from a transformer and rectifier, I would have my capacitors smoothing the output, and I've tied back to a common point so that any high power currents are not involved in my monitoring. I've already alluded to this several times, that the voltage drop across a piece of 18, 16 gauge or even 14 gauge wire is quite significant when you start talking about a few amps. And when you're measuring things like 100 millivolts or 500 millivolts, the difference that the piece of wire can make that's also ends up being included in the measurement can be quite significant. So it really doesn't pay to be lazy about how you wire things up. Make sure that you have the power supply, the main power rail, wired separately to your analog control circuitry. All right, you'll get a lot less hassle that way. So what does this all look like? Well, I put it up on a breadboard. It looks a little messy, so apologies for that. Just making do with the components that I've got. So I'm using a TLE 2142 dual op-amp for the op-amp control for both the current and the voltage. So here is the circuit. Let me just zoom in a little bit there so you can see it a little more. Okay, so the chip right in here, this is the Ref02 5-volt reference. The output of the reference is coming out to my voltage. Let me just bring that into view. 10-turn potentiometer. I've put a V on it so I know which one's which. And then the output, the wiper of that potentiometer goes across to the op-amp on this brown pin at this near side of us. The current output, if you notice underneath here, let me just move that out of the way, is a 1, 2, 3, 4, 5 100K resistors that I put in series. Like I said, I didn't have a 500K, so I've just chained these around. That's one of the nice things about breadboards. And then it's tapped on here to the input of the current potentiometer, and I put an I for current on that one. And the wiper of that one goes to the positive input on the other second op-amp input over here. I move the wire out of some of the wires out of the way. Okay, and then the output of that op-amp is through this diode right here, which is the 1N4007, I think it is right now, and then this 100 ohm resistor to the gate. Now the op-amp channel 1 on this side, you've got the wiper from the potentiometer coming in. You've got the feedback here, which is this orange wire, going to the 10-to-1 divider network over here. I'll talk about that in a second. And where it's common, feeding out to the gate. So I've got a wire, this white one, feeds out to the gate of my MOSFET. Right, so the 100 ohms and the 10K both terminate together on that pin, so that the current side can pull this voltage down easily, because it's obviously 100 ohms versus 10K. There's no competition about which one's going to win on that pulling contest. I've got my oscilloscope connected, measuring the gate voltage. I have to have a lot of meters on this one. I've got one channel on my oscilloscope measuring the output of the MOSFET. I've got the other channel on my oscilloscope measuring the gate voltage right here. Okay, so let's just go back to the circuit. Okay, so what we have here is this resistor chain here. You can just about see it quite, I think, reasonably clearly, is my 10-to-1 feedback. So this is a 100K, 10K, 1K, 100 ohms and 10 ohms to ground. So I'm using this green wire here is feeding from the top of my load to the voltage divider network so that I can feed the negative input of the channel 1 of the op amp. My power network, I'm just going to zoom out a little bit so that you can see it better. Okay, so I have the output from the MOSFET coming here. This is a 10 ohm power resistor, and I wanted more than 10 ohms because things started to get really hot, and so I just wanted to limit the current a bit more so that I can get more voltage out. I then have a series, and they're a little brown right now because they've been getting toasted, of 2 ohm resistors to give me another 10 ohms. So I've got 20 ohms in series here for my load. Now this little beauty just here, this right here, is a Vishay 100 milliohm. There we go. It's a Vishay 100 milliohm current shunt sense resistor. It's got Kelvin connection, so it has 4 pins. Just moving that out of the way so maybe you can see. And what you do is you feed your current through the outer two. So you can see the end of the resistor chain here. It's sharing the same pin as the one end of the Vishay current sense resistor. The far end has got this black connector which returns back up to the negative side of my power supply. And then in the center here, if I just move this, I've got a few things tapped off here. Right now I've got a differential pair going to this panel meter here, which is currently showing 498 milliamps. So these resistors are going to be a little bit warm. Ow. The second panel meter here is actually connected to this red point here, all right, which is you've got a 10-to-1 at this point, you have a 100-to-1, and then you've got a 1000-to-1. So 20 volts will end up with 200 millivolts on here. So I've got a 0 to 200 millivolts for my voltage and a 0 to 200 millivolts for my current displays here. All right. Now these are just 2 displays that I got from Element 14 for this project to use as an example of low-end displays and how easy you can put them together to monitor things like power and current and things like that. So these have 5-volt supply rail provided separately from my power Keithley power supply, and they have the ability to have a differential input, which makes them ideal for this because I can put the positive and negative in positions where things like current shunt resistor offsets at higher currents have no effect on them. So what I've also done here is the current output from my shunt is also tapped off here. I have it going up to a Panel Pilot ACE display that I've configured to show me the volts and current as well, and I've also got it feeding back into my op amps for the feedback. Okay, so as far as metering is concerned, I've got, like I said, one of the things I said before, and I'm going to say it again, you can never have too many meters. All right. So I'm not going to keep going back to the circuit. I'm just going to bring these on. So excuse the beep for a second while I turn these on. Okay, so right now everything is dialed down to 0. Well, sorry, my current limit is set to maximum, and my voltage limit is set to minimum. So as you can see on the output, I have 0 volts, 0 current. Okay, let us begin. As you can see from the display, this is my V set point, which is on the positive input of the voltage control op amp. It's currently reading about 9 millivolts, which of course is not enough to do anything. My I set point is set to max, so it actually, my 10-to-1 ratio is actually working out pretty good. My little stickers aren't deciding to stay on here. Maybe that was a bad idea. And my I output op amp, remember, it's not reaching, the negative input is not, there's no volts on the output, therefore the negative input of the current op amp is way below the 500 millivolts, so therefore the output of the current op amp, which I'm showing on this meter, is set right up at almost a positive rail at 29.1 volts. So if I start to increase my V set point, remember my current is set for a 5 amp current limit right now, so I should have no current limits whatsoever. I'm going to start increasing this. My oscilloscope currently showing my gate voltage on the MOSFET as being 132 millivolts. Just wanted to let you know what that's doing as well. So I'm going to start now increasing the V set point. So I'm going to take it up to effectively 100 millivolts, which should represent about 1 volt on the output, because remember, this feedback is a 10-to-1 ratio. So I'm right in the bottom end of this 10-turn potentiometer. All right, so that's 1.025. So that should be roughly 1 volt coming out. If you look at my monitor down here, it's actually showing I've got 0.92. Now this Panel Pilot Ace, it's not differential input, so it does have some effect, especially at the lower end, due to the 0 volts not being referenced correctly to the analog circuitry. So it will read a little bit inaccurate down at this bottom end. As you can see, even though I'm now voltage controlling, my current output VI set point is still set to 500 millivolts, which represents 5 amps. And therefore the output of that op amp is still set to 29 volts. Now you can see here that this is working properly. The diode is protecting things from happening, because my oscilloscope currently says that the gate voltage is 3.5 volts. All right, so 3.5 volts into the gate is giving us roughly 1 volt out of the MOSFET. So let's just start cranking this up a bit. I'll take it up to 5 volts now. Like I said, I'm not using precision resistors or anything like that. So there will be some errors in the measurement circuitry and the feedback loop. So it's, you know, if we're within a few percent, then that's perfectly acceptable based on the components that I'm currently using. Okay, so I've set basically 499 millivolts on the positive input of the voltage op amp. That, because of the 10-to-1 feedback, should give us roughly 5 volts on the output, and it does. All right. Now, as I said before, I've got a 10 ohm load. Now this is probably not better than 5 to 10% accuracy on this resistor chain. So I should be getting roughly 250 milliamps, and I'm actually getting 248 milliamps measured. And if I look at our power supply, it's actually saying that the 30 volt rail is having 257 milliamps drawn out of it. Now with 5 volts on our output, our MOSFET gate is now sitting at 7.88 volts. So it's still about this 3 volt difference between the output and what the gate has to be in order to get that output at 250 milliamp. Remember, the V threshold for these MOSFETs is typically somewhere between 2 and 4 volts. I found that they're nearer to 2 volts for when they start to turn on. And as I said, you know, if you think of them as a voltage controlled resistor, I've increased the gate voltage from the source to the gate in order to get about 250 milliamps out of this thing and maintain the output at the 5 volt level. So we've got 7.887 volts on the gate. You can see here that my V set point is still 500 millivolts. My I set point is still 500 millivolts, so it's wanting a lot more current, but of course it can't get it because it's not the one that's totally in control here. And the output of the I op amp is still sitting at 29 volts, which means it's trying its hardest to increase the output voltage. Because of the diode, it can't. So let's start increasing this now. Let's just take it up to a volt on the V set point, which should give us 10 volts on the output of the MOSFET. So 1 volt on the V set point, we've got 10.14 volts on the output. So that's still, you know, with everything else, it's still within 1%, or well, slightly over 1%. I've now got 13.2 volts on the gate. See, my current is now increased to half an amp because I've got 10 volts into 20 ohms, so that's half an amp. That's corroborated by the output of my Keithley power supply, and I've got 13.2 volts now. So the voltage output has now increased on the gate source voltage of the MOSFET. And as I said, you have to increase the differential in order to get more current flowing through those things. I'm going to take it up and see where the voltage output now stops to increase. So we're 12, 13. So that's 20 volts on the output. You've got 2 volts on the VSET. The output of the I op amp is still at the top rail. I got 23 volts on the gate. So let's take it up even further. 22, 23, 24, 25. All right, it's stopped there. I cannot get above 25.8 volts on the output. And the reason for that is this. I have a 30 volt supply. The output of the V op amp is sitting now at 29.21 volts. There's not enough output to get this thing to where it needs to be to get any more than 25 volts. So voltage set is 2.54, so I should be getting 25.4 volts, allowing for gain differences. I've got 25 volts on the output. My output of the V op amp is now sitting at 29 volts to get 25.8. So let's just say 26. So that's that 3 volt differential again. So I mentioned in the blogging on element 14, for those that are following there, what was one of the flaws of this circuit? Well, there's one of them. All right, you've got 3 volts being lost between the input of the MOSFET and the output of the power supply. So the only way that you're actually going to be able to get more output from this is to increase the supply of your overall circuit. So I'm just going to turn this off a second and put a couple of jumpers in on my power supply and see if I can give it about 30, let's just say 36 volts. Okay, now figured out how to get my power supply to give me up to 60 volts. I've just put the two 30 volt channels in series, so now theoretically I can have 60 volts at 1.5 amps. 1.5 amps being the limit of any one channel, and they're in series, so that doesn't change anything. The output is turned on, but right now I've got the volts cranked right down so that I don't start overheating resistors right off the bat. I think what we'll do after this video is I may well just flip across to doing my DC load so that I can have a way of controlling the current on the output of the power supply without having to have a whole bunch of resistors and trying to, you know, just make do with the limited set that I have. With the DC load, I'll be able to basically dial in any current I like and better monitor the capabilities of the output stage of this power supply. Don't forget though, you know, this is all on a breadboard, so there's also issues because of all the junctions. You know, nothing is soldered here. There's just all push fit connectors and everything else, so you're going to have little voltages being lost here, there, and everywhere. So that again will add to the errors that are being seen here. So anyway, enough of my bantering. Let's get this and start cranking the volts up again. So let's just right away take it up to 20 volts, which is where we were before. Now remember, we basically, with 30 volt power supply, we kind of capped out at a 26 volt output. So we're at 20 volts now. Let's keep going. Alright, so my gate voltage is now sitting at 26 volts and I've got 23 volts there. Gate voltage is sitting at 29. I've got my 20, so we're roughly about where we were capped out before. I've added an extra 6 volts to this. So let's just keep going, and as you can see, we're starting to get towards 30 volts. So there we have our 30 volts. And of course, now the reason I can't really go much more than this with the setup I currently have is I've got a 20 ohm load. I don't have any more power resistors to be able to bump that up further, so if I go a little bit more, my power supply is just there, tripped into constant current mode. Okay, 60 seconds later, I've reconfigured this panel theoretically to read up to 5 amps and up to 40 volts. So let's just crank up the output again and see if we can get it to read above 30, sorry. So 20 volts, 26, 27, 28, 29, 30. There we go, much better. So we're capping out now around about 30 volts, and the output of the op amp on the oscilloscope is telling me that it's at 33.9. And of course, it's because we've gone into current limit mode. The output of the DC power supply that I'm using to source all of this is also dropping its output just below 35. So that pretty much shows that, you know, it's easy to overcome one minor limit. If you want 30 volts, you're going to have a main VCC rail of 3 or 4 volts above that. Now it typically pays to have this anyway, because you want to be in, you know, enough of a drop across your output stage to avoid things like ripple getting reflected in your output and things like that. So now things are starting to heat up here, so I'm just going to switch to current limit. If you notice here, I've still got 5 volts on the output of my current limit on the input to my current limit op amp, meaning that I'm allowing up to 5 amps. I've got 35 volts, which is my supply rail, basically less a volt, on the output of that current op amp. Now I'm going to start increasing this current limit now, decreasing it. All right, so it's 5. Remember, we've got 1.5 amps going through this. So I'm going to bring this down. It's going to have no effect until I get about 150 millivolts reading on this middle meter right here. At that point, we should start seeing the output starting to be pulled down. So now we've got 200, which represents 2 amps, 1.9, 1.8. There, it's starting to pull it down now. So again, not precision dividers, but you can see as the op amp is nearing that, it's starting to change its output now, and it's starting to pull down that voltage. My resistors are starting to smoke here a little bit. So I'm now in current limit mode. Okay, so I've brought it down to an amp, and it doesn't matter what I do with my voltage. See here, it's still set to basically 30 volts. Right, I can change that, and it's having virtually no. Right, if I stop tweaking it for a moment, you can see the output swinging around a little bit itself, probably because these resistors are getting rather hot and changing value. I can bring that down, and it's making there. It's just started as I've gone back into the voltages below the threshold for the current that I set. So remember, 20 ohm load, so anything above 20 volts is going to flip back into current limit mode, which it is. As soon as I bring it down to less than 20 volts, it can't get it, and you can see the output. If you watch this one here, it's starting to drop down. All right, so it's because it's an amp that it wants. It's allowing the output of the current op amp to stay at 23 volts, because that's just enough, because the voltage output of the op amp now is going to be at the top of the rail. So having 23 volts there is enough to keep the op amp, the MOSFET gate input to be able to deliver the 1 amp load. So as I said, bring the volts down, it's going to go back into voltage control mode. So let's just take this down to 10 volt. My resistors are getting rather black here. Alright, so we set 10 volts. You can see here my resistors, they're starting to go a little bit brown. Okay, so we're, where are we? Yeah, so 10 volts, 20 ohm load, about half an amp. So let's just start cranking this down. Remember, this is still set for current limit of 1 amp, but you know, as I said, the feedback is a little bit off. So if I crank this down now, it should have no effect until we get to around about half a volt or 50 millivolts on this I set point. And as we approach it, it's going to start, because these op amps are not infinite gain, it's going to start pulling it down. As you can see there, all right, it's starting to pull it down as we approach it. Okay, so now it's having an effect. So I've set 50 millivolts on the input to the I set point, and I've got 400 milliamps, so it's a little bit out on this one. I'm actually reading 40 milliamps on the display that's on my breadboard as well, so that corroborates what this one is reading. The I set point, it will be interesting to see what the feedback voltage is. Yeah, because the feedback voltage is not actually differential on this current setting, so that's probably why there's a difference there. I'm setting 50 millivolts, but I'm getting 400 milliamps out. So the reason for this, if I bring in this circuit for a second, my little panel meter here that's reading 407 milliamps is measuring directly across the Kelvin connections on this resistor. The panel meter as well is basically tapped the same point on one side, but my voltage reference here, which is the positive input to this op amp, is actually between here and 0 volts. So if you think about it, I've got 400 milliamps flowing through this resistor, which means that I'm actually measuring, oops, I lost one of my meters. I'm actually measuring 40 millivolts across that resistor. Right? Now, allowing for other circuitry that's affecting this, I could be dropping easily, 10 millivolts through this circuit because of the current that I'm drawing. So that would throw off the fact that this negative rail is tied back to here. So the voltage drop that's coming across, all right, so sorry, didn't have the I'm pointing to the drawing and it's not in the view. So the voltage drop between here and the negative rail for this op amp here is currently fed back to here, all right, and the feedback is to this point on this Kelvin resistor. So the current that's actually flowing through here, this voltage drop, because this is not a hugely thick wire, is actually probably elevating the voltage that I'm reading on the back of this. All right, so even though I'm setting 5 here, this, because of the extra resistance in the wire and the elevated voltage, it's going to be messing with that and actually giving me a false reading on here. Now ultimately, you know, it doesn't matter too much what that is, because with a very basic power supply, you're not going to be measuring the set point on the input to the op amps. You're going to be looking at your display, whether it be this one here, which is telling me the 40 milliamps, all right, and that's confirmed by my power supply as well, or you're going to be looking at the output of, and sorry it's sideways here, but basically, you know, you're going to have a front panel on your power supply and you're going to be looking at this. And this also tells me, now this is differential directly across my current sense resistor, so it's going to be pretty accurate. So it's telling me I've got the 400 milliamps as well. All right. So for a basic bench power supply, student mode, you know, beginning engineering and things where you don't need super accurate, it's good enough. It's more than good enough. You know, most of the systems I build, if you're just building circuits to drive some LED displays and things like that, having even, you know, just 1% accurate, or even a few percent accurate on your power supply is perfectly adequate. You know, if you set 5 volts, TTL logic, it can take anything from 4.75 to 5.25. So if you set 5 and it's really 5.1 or 5.05, that's not going to cause you any problems. Nothing that we really do in our basic electronic work is that critical. It's only when you're going to get into precision measurements for, you know, if you want to measure temperature using resistance probes to 0.1 or 0.01%, then obviously your circuitry, or at least your voltage references and things like that, need to be significantly more accurate than that. But here, if I, you know, right now, if I just take this out of current mode again, it's just going to crank the current up and allow it to do the voltage setting, all right? I'm going to take this to say it's 10 volt. I just want to demonstrate what happens here, because remember what I said about accuracies and things. It all goes back to your precision voltage reference, and how good is that? All right, I've got 10 volts out here. So if you think, if you remember the fact that in order to control this, I have to have at least 3 or 4 volts available on top of what I want out on my main supply rail, so that my op amp can control the circuit properly. So, you know, because if I've got 10 volts, I need to have a 13 or 14 volts on the gate in order to get that 10 volts out, and we're roughly half an amp here. So I'm going to go straight to my power supply, and I'm sorry it's not in view, but I'm going to change the voltage. Right now it's 36 volts. I'm going to just instantly drop it to 20 volts and watch what happens. Take my arm out of the way. All right, I haven't done it yet. Just about to do it. Let me just bring this display back up. Ready? It's set to 20 volts. There. Going to apply it now. Okay, I just changed that from 35 volts down to 20 in a heartbeat. Let's take it back to 35 volts. You can hear the relays clicking on the power supply. All right, that's 35 volts. If you notice this voltage here and the current here, all right, you can't change that output faster than really what this is doing. It's going to drop down there in probably sub millisecond. All right, so that's 35 volts. Let me take it down to even 15 volts. All right, so I'm going to more than halve the voltage that's feeding this. All right, not even a glimmer. Now, I'm not using an oscilloscope to check the output of this. Actually, you know what? I've got one here, so why not? All right, so my oscilloscope is set to 5 volts per division because, well, we're doing 10 volts. Let me just crank it down to 2 volts. Now, what I'm going to do is, that's obviously how quickly the output shifts when I'm turning it on, but that's turning the power supply directly on. I'm going to leave the power supply turned on this time, and what I'm going to do is, let me just crank down. No, I can leave that there, I guess. It's good enough. This is 5 milliseconds per division, so that took 5, 10, 15 milliseconds to come up to voltage. There's no overshoot or anything on that. Just going to reset the scope to single, and it's currently set for 15 volts. So I'm going to change the volts now to be 35 volts on the output, and let's see what happens here. right? That didn't even trigger the oscilloscope. If I turn the oscilloscope off and back on again, there's my output. Now obviously more voltage, it came up quicker. So that's now sitting at 2 volts per division. So there you go. I've got 35 volts set. I'm drawing half an amp because the output of my power supply is still set to 10 volts. As you can see up there, it's reading 10 volts on my scope as well. So the output of my Keithley, which is supplying our power supply at the moment, is set to 35 volts. So what I'm going to do is I'm going to set my scope to run, not single, to run again. All right, because what I want to do is crank down the scale to maybe 20. I want to see if we can capture any glitches at all here. So let's just change this voltage to 15 volts again. All right, I didn't even see anything on that oscilloscope changing there. Let's go back to up at 35, back down to 15. Now if I go to 10, just because I want to actually show that it will have an effect. All right, so there, so just so you know, I'm not cheating here. You saw that go by there. Let me just go back up to 15. You'll see it come back. Oh, 5 doesn't help. 15. All right, and now the output is back to 10 volts because it's able to regulate again. If I take it up to even 40 volts, because all of the components I've got will actually handle 40 volts. All right, there's nothing. You can see absolutely nothing. It's slowly scrolling across 400 milliseconds. So it's, you know, it's a second per division. If there was going to be any change in that output, you would have seen it. All right, it's making no difference whatsoever. And I'm changing the output, the supply rail, massively from 15 volts up to 40 volts. Let me go back from 40 right back to 15, and I can't see any change there whatsoever. So anyway, that is your basic circuit. All right, couple of one dual op amp, one precision voltage reference. You can ignore the circuitry for the load, and using a couple of small panel meters for the display. Get back to them like those. These cost like, you can pick these up for maybe $30 to $60 each, depending on what kind of precision you want. These are 3.5 digit ones, so they're quite accurate. They're near the $60 mark each. If you've got a, there's plenty of multimeters that are sort of like 3.5 digit, but maybe only about 1% accurate that you can get from eBay and various other things, and they only cost you sort of like $5 and $10 each. You can also use a microcontroller A to D input and have it just drive a little LCD display, and that's one of the things that we're going to do as we start working through this, is to go more away from pure analog circuitry and more towards digital control. But as far as a student level power supply is concerned, for the main circuitry, what you've seen here today, all right, this little circuit right here is perfectly adequate. It gives you a pretty stable output. Now I haven't done a whole bunch of transient response tests on it or anything like that. Minimal amount of components, and it works pretty well. And the the MOSFET that I'm using on this is the IRFP 064. It can handle, I think, something like 70 amps. So it's going to, for anything you do with this thing, it's going to be pretty much indestructible. You've got current limit, you've got voltage control. You can control it right down to 0 volts and right up to the 30 volts if you give it 36 volts. One of the things that I mentioned before, which is kind of based on the fact that you've got to be careful of your wiring, that's as low as I can set the current right now, and I've got about 13 milliamps on the output. But if I show you what my DVM is seeing, it's actually showing I've got minus 22 millivolts. Well, of course I have no negative rail, so I can't have, there's no way that I can have a negative. But what this is actually being caused by is the fact that my negative on here, all right, this one right here, is actually a voltage differential probably of about 10 or 15 millivolts between there and the ground that this panel meter is measuring. All right. So like I said, this is part of the things you have to be aware of when you're using breadboards and you've got lots of flying wires like this. You are going to get some discrepancies. You do have to be very careful about the paths that you use for your higher current things. I mean, we don't have a lot of current here, but it's still lots of loose wires, lots of unsoldered, they're just contacts, and I'm sure some of these sockets on my breadboard are probably a little bit loose now from repeated use. So you're going to get a few little errors, and the only way to be really sure now is we know this circuit works in principle, we've seen it work, all right, is to actually build it up on VeriBoard, have proper soldered connectors, be very careful about your current paths and things like that. And then, you know, once you've got it to that stage and you're comfortable that everything's working properly, you know, if you really want to take it beyond that, you could even get some circuit boards made. And one of the things I might do later on is actually design a few circuit boards for different stages of this and make the sketches available to anybody that wants them. But anyway, as this is the basic one, student op amp, done, dusted. That's it. So the next thing I'm going to do is take this a little bit further to try and improve the ability of the current and the voltage control, so that I don't have to have the op amps running and the voltage reference running at the same voltage as the power supply. So, you know, in my blog I mentioned that there was a few things that, you know, you needed to think about with the circuit. So one of them is whatever my supply voltage is, that's also what is supplying my chips. My chips are limited right now. The op amps can only go to 44 volts. My VREF can only go to 40 volts. So if I want 30 volts out of this, I really need at least 35 volts on this rail. Now that doesn't give me much of a margin, all right? If I don't want to put a voltage regulator in here, which, you know, you can see I can do a lot with the power supply and it has no effect on the output, I do run a risk that when I first turn this on, the surge could easily go above 40 volts just for a fraction and potentially could fry these. So you really want to be able to regulate these down. But if I do run these, say I do it with, I don't know, 15 volts as an example, that would be perfectly adequate for all of these things to work well. I mean, I showed you that it went right down to 15 volts with my power supply, even with this rail working for a 10 volt out, and it was perfectly stable. But if I do run it on 15 volts here, and I've got this sitting up at say 35, 40 volts, the output of this op amp cannot get the FET gate high enough to be able to deal with that. So the next thing I'm going to look at and show you is how can you rearrange this circuit, and it doesn't take much at all to be able to do that and be able to drive this thing still up to the 40 odd volt rail and not have to have the same supply or more on your control circuitry. Because remember, if I want 30 volts out of here, I can have this rail at say maybe, you know, 30 volts or a fraction above, because this MOSFET is able to turn on to something like a 9 milliohm output impedance. All right, so it's going to basically short this rail to this, but in order to do that, this gate has to go above that. Now the only thing that has to go above that gate voltage is the output of this op amp. So if you were running 30 volts here, you could run 40 volts supply for these op amps at a low current supply and have 30 volts at a high current supply for your MOSFET, and that would be perfectly acceptable. All right, you don't have to have everything sitting at 40 volts, which would obviously increase the heat on your output. But a better option is to keep these low and modify the circuit slightly so that you can actually avoid the whole situation in the first place. Now with a N-channel MOSFET, you still always have to be able to take this above the source by 3 or 4 volts in order to get the output, which means 30 volts means at least 35 here over time. And you're not going to be able to avoid that, but there's no reason why your op amps have to be running at that same high voltage as well and putting them at risk of failing. One quick thing that I forgot to mention before I go, which was one of the other flaws of this design, and as I said, it really doesn't affect if you're measuring directly on the output what the voltage is with, say, either a meter like a DVM or something like that, is the fact that this voltage op amp here, you've got your voltage set on the positive input and you've got your negative feedback, but the ground reference for this is on the negative bus rail here. All right, it's the same basic point. So what happens is you set yourself 30 volts here, and if your meter is measuring, all right, this op amp is measuring between this bus rail basically and the positive here for its feedback. What it's not compensating for, which is quite typical in lower cost power supplies, is the voltage drop across this resistor. As you start increasing, say you've got 1 amp flowing through here, you can have 100 millivolts dropped across here. So if you've set, say, 10 volts and you want it to be fairly accurate, you're going to have 10 volts between this positive rail here and the ground rail. So if you've got 10 volts between the positive output and the ground rail, what you're going to measure actually across the terminals here is 10 volts minus the drop across this sense resistor, which is 100 millivolts if you've got 1 amp flowing through here. Right? So you're actually going to have 9.9 volts across here. Now if you have 5 amps flowing through this resistor, that's 500 millivolts here. So even though you think, if you're measuring between here and ground with your multimeter, right, it's going to tell you that you've got 10 volts, but the reality is right on the output pins here, you're only going to have 9.5 volts. Now the only way around that, which is what I've got with, these two little panel displays here, is these are differential. So I can, even though they're running on a 5-volt rail, which is also referenced to this ground point, its inputs are differential. So I can actually connect one input right here and one input right here for my current sense. So nothing that is in the power supply high current path has any effect on its readings. And for the voltage meter, I can have a 10 to 1 or 100 or 1,000 to 1 divider, so that I've got 30 volts here and I'm reading the 30 volts on my little panel meter, but I'm measuring right across here, because even though this goes up by 500 millivolts from the ground reference, the differential inputs on these little panel displays can allow as much as 2 volts difference between the ground rail and the differential inputs. It's common mode rejection, which allows it to be measuring and compensating automatically for the fact that this is putting a bias on the output. So if you're actually just turning a potentiometer and setting the output to what you're reading on the meter, then you will get out what the display shows. But if you're using something that is based on the negative supply of your power supply, then what you're getting out is not necessarily going to reflect what you want. You're going to have to compensate for the voltage drop across this resistor. So that was the last thing that I wanted to mention. All right, remember I said there was a few things that was wrong with this circuit. Again, not critical, just things that can be compensated for with a more advanced circuit. Drop across the current sense is not compensated for. Your op amps are running, and your precision voltage output is running off the same supply as your main power circuitry. Your output of the op amps, if you want to go rail to rail on the output of the power supply to your main rail, then the op amp outputs have to go above that in order to get this output to work properly. So that's your 3 main things there. And the last one, of course, is you just got to watch out where you put your current path, so that your analog circuitry for the control loops are not getting affected by the high power paths. Anyway, that's it. I just wanted to mention that. Thanks very much. Bye.